Good afternoon, friends. The session today is on demonstration of QGIS software. This is the second session. First session was taken by Kapil Oberoi on familiarization with QGIS. Today I will talk about plugins, projections, and how to perform georeferencing using QGIS. My name is Prasun Gupta. I am with the Geoinformatics department here at IIRS. So the things we will be covering today are the plugin architecture, that is how to install and use georeferencer and open layers plugin, how to georeference a topographic sheet, and at the end we will see, once the georeferencing has been performed, how to reproject the topo sheet to another projection system. The software that we will be using is QGIS 2.4. This can be freely downloaded from this website qgis.org. The data for today's demo has been shared with the coordinators. If you are accessing or attending as an individual, you can download the data for today's exercise from this URL www.libdot.utexas.edu/maps/ams/India. Here, old topo sheets uh, are placed in .jpg format. So the topo sheet in which the Dehradun area lies has the name nh4405.jpg. You can download this image from this link, and you will require the software. I think you have already downloaded and installed it if you have done the first day's exercise. So this is the software, this is the data, and let's see how we deal with plugins. So once you open QGIS, you may require to close the extra menus because these we will not be using in the exercise. The first one is the shortest path plugin, which occupies your lower left hand side of the QGIS software. You can simply click on this cross sign here and close this box. It can be opened later, and since we are not using it in this exercise, we will close it. Second, we will also not be using the processing toolbox. So that is on the right hand side pane. So you can simply click on this close icon here and close this processing toolbox. And you may also not require this browser plugin inside QGIS, which can also be closed. These can all be reopened from the view menu. If you click view and panels, all these can be reopened. What we are interested in today is the plugins. So to access the plugins, to modify them, to see which are available, you have to click on this menu option which says plugins. Once you click on plugins, there will be a drop down. You have to select the first option which says manage and install plugins. Why we are going here? Because we require the georeferencer plugin which will do the georeferencing. The georeferencer plugin is by default already installed. It just needs to be enabled. So once you click on manage and install plugins, a box with the title plugins will be opened. If you click on this all option and then type in the search box here Just click there, and if you type georef, GEOREF, you will see two options have come. The first option is of interest here, georeferencer space GDAL. This is the plugin which will help us do the georeferencing. Initially, this box here will not have the cross sign. You just have to put a cross here and say OK on the bottom left hand side. So what we are doing here is we are searching for the georeferencer plugin and we are enabling it. We are putting the cross sign, that means we have enabled it. So the steps are also given here. Type in the search box georef and make sure the X sign is there next to georeferencer space GDAL. Now this is a one-time process. You need not do this every time you open QGIS. You have to go to plugins and manage plugins and enable this. Once you have enabled it, it will remain so. If you want to disable it, or if you want to update it or uninstall it, then you need to come back to manage plugins. Otherwise, this is only a one-time process and you may not need to repeat this. Once the georeferencer plugin is installed, the next plugin that you will require is the Open Layers plugin. Now this is an optional step. You may not require it to actually do the georeferencing step. But to check whether the georeferencing has been done correctly, you can check that by overlaying the georeference layer with, let's say, Google satellite imagery or Yahoo satellite imagery. To overlay that, we can use this plugin called Open Layers plugin. Now to use this Open Layers plugin, as it is obvious you are using Google imagery which is coming online, you will require internet connection for this. However, if you do not install this plugin, you do not require an internet connection. But if you want to install this, you make sure internet is on. Type in the search box Open Layer, which is one word. There is no gap in between. There's no space in between. Just type OPENLAYER in one continuous fashion. And you will see a second option, Open Layers plugin has come. Just click on it, and then on the bottom right hand side, the button will get activated, which is Install plugin. Once you install it, it will download a very small 300-400 KB file and it will go into the QGIS setup and it will be enabled by default. Once your georeferencer and your Open Layers plugins are activated, we can start with the georeferencing process. Just in case you get an error, something like this, which says plugin installation failed, plugin not found. This ideally, or this generally comes when the internet connection is not working. So make sure that the internet connection is working, and when you are going to install this plugin. Once the plugin is installed, you can click on this close button here and close the plugins dialog. What you should do now is open the georeferencer plugin. Now where would I find the georeferencer plugin? It is under the raster menu. In the menu bar, there are many options. We clicked on plugins to activate the plugins. Next to it is vector, next to it is raster. On the raster menu, if you click on the a drop down will appear. The second option says georeferencer. Is another sub menu, georeferencer. Click on this button here to activate your georeferencer. Once you click on it, a box will open and we will see the options in some time. Before that, let's go through what is the definition of georeferencing. Georeference means to associate something with locations in physical space. The term is commonly used in the GIS field to describe the process of associating a physical map or raster image of a map with spatial locations. This basically means that you have a physical map or an image, or let's say aerial photograph or a satellite image, which you wish to associate it with the spatial location. That process of associating the image or map to the spatial location is called georeferencing. What is the use of georeferencing? Once you have added any data and you have assigned spatial locations, then you can overlay with other data sets that you have already georeferenced, or other data sets which are already georeferenced. These can be overlaid, and spatial analysis and other such GIS tasks can be carried out. So this is one of the first steps in doing your GIS work. Some other basic concepts you should, in the second module and in earlier lectures, you must have gone in detail about projection systems. In literature, there are other terms used for projection systems such as coordinate reference system or CRS, or spatial reference systems or SRS, and other words. In QGIS, you will find this term CRS being repeated many times, which basically refers to the projection system of the project. The second basic concept which should be clear to you is the conversion between degree minutes seconds to degree decimals. So I'm sure most of you are must have had geography in your basic courses, and you know what is degree minute seconds, that is specifying a latitude or a longitude in degrees, minutes and seconds, or which can be specified as a floating or a real value, which is a degree decimal. So if you have to convert a degree minute second value to degree decimal, the basic conversion formula is based on unitary method. 1 degree is equal to 60 minutes. So half a degree is 30 minutes. Example, if 10 degrees, 30 minutes has to be written in, so this is in degree minutes, 10 degrees, 30 minutes has to be written in degree decimal. This can be written as 10.5 degrees. So 30 minutes is 0.5 degrees. So that gets appended to 10, hence 10.5 degrees. Similarly, 20 degrees 15 minutes can be written as 20 degrees and 20.25 degrees. 30 degrees 45 minutes can be written as 30.75 degrees. So these are some of the basic concepts. Now to start the georeferencing process, we saw you have to first activate the georeferencing plugin by going to plugins, manage and install plugins. Once the plugin has been activated, you click on raster, go to georeferencing and click on georeferencing. This will open a new box. On top of it will be written georeferencer. Here you click on the file menu and select the first option which says open raster. Once you click on this, another dialog will open which will ask you to select the file, navigate to the folder where you have kept the data which has been given for today, or you can select any other topo sheet if you have already scanned with you, or an image of a topo sheet which is already there with you, or the exercise data which has been shared with you, nh4405-cut.jpg. Just navigate to the folder, click on the file and click on open. This is we are adding the scan topo sheet inside the georeferencer plugin. Next, once you add it, either of the two things may happen. First, you may get a dialog asking to select a projection system or CRS. This will happen mostly in earlier versions of QGIS. In more recent latest versions of QGIS, this option number 2 will take place. But in the earlier versions, if you have installed 1.8 or 1.9 or 2, this step will happen. That is, a dialog will pop up and it will ask you the projection system. If you have the newer version, a yellow colored bar will pop up on the top of your QGIS software and it will be written that the CRS has been defaulted to the system CRS or has been defaulted to CRS 4326. Now that is the EPSG code. Now we will talk about these codes in further slides. Now in case you have come across this first box which is asking you to select the CRS system, just type in the filter box 4326 and select the projection system which is latitude longitude WGS 84. Now what are EPSG codes? EPSG is an acronym which stands for European Petroleum Survey Group. This is an international body which has assigned unique numbers to all projection systems known. So there is a unique number given to each and every projection system. So for example, the most common projection system used generally is lat long in WGS 84, which has the EPSG code 4326. This is the way it is written, most commonly written, EPSG colon N, where N is the unique number which I am talking about. So EPSG colon 4326 is the CRS, most common CRS. There are other ways in which it is written. The other most common format is called the proj.4 format. The area marked in red on the right hand side is how it is written. Within single quotes, projection is equal to lat long, datum is equal to WGS 84 and no other definitions. The third most common way of writing it is the well-known text format or WKT format. This is an OGC specification. You may have already come across the term OGC, which stands for Open Geospatial Consortium. This is again an international body which sets standards for softwares and file formats and other GIS related technologies. So OGC is a well-known text format for specifying lat long in WGS 84 datum is given in this box marked as red. In most cases, you will only be required to remember or use the EPSG file, the EPSG format, where you only need to remember the number, the EPSG code given to the projection system that you are using. So as I said, in the filter box, just type 4326. On this portion here, there will be many entries. Once you type this, they will all be shortlisted and only one entry will remain, which says WGS84 here. Just left click on this once and then click on OK. So there are three steps when specifying the CRS. First step is that you have to click on the filter and type 4326 in this box here. Second, you have to click on the CRS which is displayed. So you have to click on this area here and then you have to click on OK. So doing this, you are specifying the projection system in which the topo sheet is. In case your image that you have added or the topo sheet you have added is in a different projection system, you can search for your projection system by typing the keywords in this filter box here and select the correct projection system for the image. Now, once the projection system for the topo sheet has been defined, next step is to identify the four corners of the topo sheet. They are also called the tie points or the control points. Now, first thing, you click on this magnifying button here in the georeferencer tool where the topo sheet has been added. Click on this magnifying button here and then click and drag on the lower left hand side where you can see the coordinate 30 degrees and 78 degrees written very clearly. For your convenience, the image which has been given to you, the area has been marked with a big red circle so that you do not have a problem identifying the point. So zoom, click on the magnifying glass and zoom to the point which is marked as P1, which is on the lower left hand side of the topo sheet provided to you. Next, you have to click on Edit, Add Point. The first option after you click on the menu option Edit, select the first option Add Point. Then bring your mouse precisely to the point where this line and this line are intersecting and click on it once. A left click on it once, that's all. As soon as you click on it, another box, something like the one displayed below, will appear on your screen, which says enter map coordinates. Here you have both the options. In case you have the coordinates in degree, minutes, seconds or in degree decimal, you can add in both formats. The instructions are written here, but in our case we will convert the coordinates to degree decimal and write in these two boxes. So in this case, the coordinate is 78 degrees east and 30 degrees north. So we write in this box X or easting. We write in this box 78, and in this box Y or north we write 30. Most beginners make the error of writing 30 here and 78 here. Just be careful. The first value that you write here, the X, that is the X value or the easting value, in this case is 78, and the Y or the northing value here is 30, that is 30. Once you type these two values, just click on OK. So this is how you are giving the first tie point. Now, the example which is being shown today is that of a topo sheet. Here the tie points are marked on the map that you are using. But there may be cases where a map has been prepared by your friend or by some other organization and you need to georeference it. Or you have an image which is taken from a platform, something like an airborne platform, a aerial image, or a satellite bound platform. It is a satellite image and you need to georeference it. Then how do you do that? You have to select features that are clearly visible on the image and those which can be identified, and the same features can be identified on the ground. So you need to identify the feature on the image, go on the ground with your GPS or a GNSS receiver, take the reading on the ground for that feature, come back to the lab, identify the feature on your image, click on it, and enter the coordinates that you have taken from the ground. Now there are some basic principles that you have to keep in mind when selecting these features. The first thing is that they should be invariant features. That means they should not change with time. Try to avoid natural boundaries and intersections such as forest boundaries or agricultural plot boundaries or river bends, etc. Try to take man-made features such as road, rail, canal, intersections, or building boundaries. These do not tend to change with time, whereas these boundaries tend to change with time. Next common thing which you need to know is the minimum number of points required. So in a flattish terrain, a minimum of 4 points which are spread out. These 4 points should not be concentrated in a small area. They should be spread out throughout the image at preferably all the 4 corners, or try to take the 4 points as widespread as possible. But this is the bare minimum which is required. More points may be required for more undulating terrain if you have. So in our case, we are just taking 4 points. The first point which we added, P1, which was on the lower left hand side. Now use these tools, zoom out using the negative or minus magnifying glass, or this button here which says zoom to layer. Use these and the magnifying glass. Use these tools to zoom to the next point which is on the lower right hand side corner, which is marked as P2 with a big red circle. And you will see there is another intersection of 2 lines here. Repeat the same steps, that is, click on add, edit add point, click on the crosshair, and then type the coordinates 78.5 degrees east and 30 degrees north. Once you click on this, click on OK. Then again zoom out, zoom into the top left corner. There will be a point P3. Yeah, top left corner will have the point marked as P3. Zoom into the crosshair, click on edit, add point, click on the crosshair, type these readings 78, 30.5. Again zoom out, go to the top right corner, zoom in, see the point P4, identify the intersection and click on it, and then type the point 78.5 and 30.5 respectively. Once all your 4 points are given, on the table below, or also called the GCP table, it will look something like this. 4 points will be enlisted. The source X and Y and the destination X and Y will be written. And what is of importance here is the residual in pixels given here. So this value will tell you whether your georeferencing is going to be correct or not. If there is a high value here, that means there is something which has gone wrong when specifying the 4 coordinates. Maybe you have not clicked at the correct point, or maybe you have given the wrong coordinates when entering them or typing them. So just check them. Whichever point has the highest residual possibly is the wrong point. Just select that and delete, or just removing this cross means disregarding that point. So at the end of the process, you will have 4 points and the residual should theoretically be less than 1 pixel. That will give you good georeferencing. Now, once the 4 points are given, the next step is to actually perform the georeferencing, or what they call it in QGIS as do the transformation and then create a new file. Now, how to do the transformation? We have to first put some settings. That is, you have to click on this button here, a menu item here which says settings, and select the option transformation settings. Once you click on it, a new box will come. The first option you need to specify as thin plate spline. The option is for the transformation type. There are multiple options here. We will discuss in the next slides. So transformation type has to be thin plate spline. The next option, resampling method. Keep the default as nearest neighbor. The third option, which is compression, keep the default as none. So you need to only change the options which are shown in the red boxes. That is, in this box or in this drop down, select thin plate spline. In this option here, output raster, click on this button and specify where you want to save and what is going to be the output file name. And in the third option, which says target SRS, click on this button and select EPSG 4326, that is lat long in datum WGS84, as the output projection system. Also put a check on this box at the bottom which says load the layer in QGIS after completion. So once you click on settings and transformation settings, you need to do these 4 things. First, change the transformation type as thin plate spline. Select the output raster as modified, or give the output file name as modified.tif. Here you can give any file name as you prefer. Select the target SRS or the output coordinate system as EPSG 4326 and put a check in the option which says load in QGIS and click on OK. Now, talking about the transformation types which are available with QGIS, here I showed you that we used thin plate spline algorithm. There are other options also available. The first option, which is linear algorithm, is used to create a world file. That is, the coordinates that you created will be saved in a text file. And this does not actually transform the raster. It only saves those coordinates that you have given into a .wld or world file. This algorithm likely won't be sufficient if you are dealing with scanned material. So this is only a basic step. If you wish to save the points which you have done, you select the linear algorithm and you perform the transformation. The second option available is the Helmholtz transformation. This performs simple scaling and rotation transformations. The third is polynomial algorithm 1, then polynomial algorithm 2 and polynomial algorithm 3. These are actually the most widely used algorithms for georeferencing, and each one differs by the degree of distortion introduced to match the source and destination control points. The most widely used polynomial algorithm is the second order polynomial transformation, which allows some curvature. First order polynomial transformation, that is affine, preserves the collinearity and allows scaling, translation and rotation only. The fourth transformation type, that is thin plate spline algorithm, is a more modern georeferencing method which is able to introduce local deformations in the data. This algorithm is useful when very low quality originals are being georeferenced. So we've used this one in the example given today. The last algorithm which is available is the projective transformation, which is a linear rotation and translation of coordinates. In terms of resampling techniques which are available, they can be mainly categorized into three categories: nearest neighbor, bilinear and cubic. We will see the advantage and disadvantages of all three. So what is nearest neighbor? Nearest neighbor assignment is the fastest resampling technique and is appropriate for categorical or thematic data since it does not alter the value of the input cells. Since the output cell value remains the same, nearest neighbor assignment should be used for nominal or ordinal data where each value represents a class, member or classification. This may be categorical data such as land use, soil or forest type. So generally what happens in nearest neighbor is whatever is the cell value after the transformation has been taken place, the new cell value, to assign a value to the cell, the cell which was closest to it in the original is found out and the value from the original cell is copied into the new cell. There is no arithmetic or no calculation which is performed, simply the old value is copied into the new cell. Whereas in case of bilinear interpolation, the value of the 4 nearest input cell centers are used to determine the value of the output raster. So to find the value at the output cell, 4 nearest input cells from the original data are determined and their weighted average. The new value of the output cell is the weighted average of these 4 values, and it is adjusted to account for their distance from the center of the output cell in the input raster. So the nearest 4 input values, their values are averaged based on distance weighting and the output value is found out. This interpolation method results in a smoother looking surface that can be obtained using nearest neighbor as compared to the output which is obtained using the nearest neighbor algorithm. Now, since the values for the output cells are calculated according to their relative position and the value of the input cells, bilinear interpolation is preferred for data where the location from a known point or phenomena determines the value assigned to the cell. That is in case of continuous surfaces. Now imagine elevation, slope, intensity of noise from an airport, the salinity of the groundwater near an estuary are all phenomena represented as continuous surfaces and are most appropriately resampled using bilinear interpolation. So since bilinear interpolation depends on the cell value and the distance from it, any phenomena which changes with distance or can be represented as a continuous surface should use bilinear interpolation as its resampling technique. The third and final category of resampling techniques is called cubic convolution. It is similar to bilinear interpolation except the weighted average is calculated from the 16 nearest input cell centers and their values. In case of bilinear interpolation, 4 nearest input cell centers were used. In case of cubic convolution, 16 nearest input cell centers and their values are used to calculate the output cell value. Cubic convolution will have a tendency to sharpen the data. In case of bilinear, the data was smoothened. In case of cubic, the data is sharpened. Therefore, the resampling method is often used when resampling imagery such as aerial photograph or satellite image. So in case you are working with aerial photograph or satellite image, cubic convolution is the best option to choose in the resampling technique. Now let's go to the final steps of doing the georeferencing. So we added the 4 control points and we set up some settings. Now the final step, that is clicking on file and start georeferencing, will actually create the new file and it will add it to the QGIS interface. So you have to click on file and start georeferencing. On completion, the georeference topo sheet will be added to your QGIS map canvas. You can close the georeferencer. Once you close the georeferencer, it will ask you whether you wish to save the GCPs. You may wish to save it. It is not mandatory. It is optional. Now, to verify whether the georeferencing you have done has taken place correctly, you can overlay this with a map which is available through the Open Layers plugin. Now this verification step, that is from here onwards, you will require an active internet connection on the system that you are doing it. If you do not have an internet connection, then these steps are not possible to be performed. So to verify the output, click on Web, Open Layers plugin, then OpenStreetMap, and then you can select either OpenStreetMap or you can select Google Layers. You can open Google Maps inside QGIS or Bing Map inside QGIS and verify whether the topo sheet is overlapping with the area which you can see in your Google imagery. In many applications, the topo sheet or the imagery which you have just georeferenced may need to be projected or may need to be saved in a projected coordinate system such as UTM. Your lat long is a geographic coordinate system. In many applications, the coordinate system may be different. So QGIS supports exporting an image or exporting the topo sheet in multiple projection systems or in different projection systems. Now how to do the image reprojection? Simply right click on the layer. Once you have displayed the layer, just right click on it and select the option which says save as. Once you select that, you will be allowed to change it to UTM or any other projection system. Before I show you that, uh, I need to just let you recapitulate what are the UTM zones of the world. So as you can see, the entire globe is cut out into equal size grids where each grid is given a number. So this all the areas lying on this column here belong to UTM zone 1. All the areas lying on the second column is UTM zone 2, and so on, 3, 4, and so on. So India more or less lies from UTM zones 43 to 45. A little bit lies in other UTM zones also. So in our case, it lies in 44 north. So once you click on save as, you will get a box like this. You again need to do three things here. First, click on browse and specify where you want to save the output. Now remember, this output is going to be used in tomorrow's exercise also. So make sure you remember where you are going to save this. So click on browse and give the name of the output file. Second, click on the button which is just below browse, looks like a small globe. And here you specify the EPSG code 32644. This is the EPSG code for the UTM 44 North and WGS 84 datum. Okay, so click on this button here. You will get another box which says coordinate reference system selector. Type in the filter box 32644, that is 32644, which is the EPSG code for UTM 44 North in WGS 84 data. So click on this filtered text and then click on OK, and then finally click on OK again at the Save As dialog. Once you click on this, your final resultant file, which is projected.tif, will be opened inside QGIS. If you want to further verify it, you can I would always suggest that you create a new project. Do not add the projected file to the existing project. Click on new project, then add the new file which is projected.tif and hover your mouse over the image, and at the bottom of the software QGIS you will notice the coordinates. This will be a large 6 or 7 digit number which will be in meters. That is your projected coordinates. Further, you can check whether your output is correct by right clicking on the layer, going to properties. Once you click on properties, this box will open, layer properties. Take the last option, metadata, and here there are many sub options. Select the last sub option which says properties. Scroll down and you will see an area which says layer spatial reference system, and you will see here the spatial reference system is written in the proj.4 format which I discussed to you initially. So you will see projection written as UTM 44 North, datum as WGS 84 with no other definitions. So this is the final way you can check your georeferencing has been done in a correct manner. So that is it for today. We will take some questions. In case you are interested in taking down my email ID and asking questions later, please note it down. It is prasun, prasun @iirs.gov.in. So we will take a 5 minutes break and then we will come back to take further questions. As I see them in my screen here. The first question is, can you show once again how to install georeferencing in the Open Layers plugin? So let's go back to the slide where we open the plugin architecture. I think, yeah. So once you open the QGIS software, you have to click on this menu option which says plugins, and then select the first option which says manage and install plugins. So after opening the QGIS software, QGIS desktop. So sometimes once you've installed it, you may see two icons in your programs or on your desktop. One which says QGIS desktop, one which says QGIS browser. We are using the QGIS desktop version to perform the georeferencing. Once you open the QGIS software, the option on the top which says plugins, just click on that. A drop down will come. Select the first option which says manage and install plugins. As soon as you click that, a box will come which says plugins on the top here. Now, if you do not have internet working, you may not be able to install Open Layers plugin, but you can still work with the georeferencer JDAL plugin and do the georeferencing exercise. You need the Open Layers plugin only to cross-check whether the georeferencing has been done correctly or not. To actually perform the georeferencing steps and create a georeferenced map, you do not require the Open Layers plugin. So all you need to do is click on plugins, go to manage install plugins, type here georef, and you will see option georeferencer space JDAL. Just enable that, click on the check box here, and you will be able to use the georeferencer plugin. The georeferencer plugin will appear in the option you have to again close this box. You have to click on this menu option raster, and then you will see an option georeferencer, and then another option georeferencer sub option. Select that, and then you can continue by adding the topo sheet, adding the 4 coordinates, and then doing the georeferencing procedure. Hope I have answered your question. Now, the next question is how to find out the UTM projection for any place in India. A very good question. If you simply search for UTM zones in the world on Google, you will see a very big gridded map. I think I showed. Yeah, you will see an image something like this. Now, how is this zonation done? So starting from the 0-degree line, or starting from this, can call it minus 180 or plus 180, they are both the same line. Starting from this line, at the equator, at every 6 degrees, a new line has been drawn. So the entire 360 degrees has been divided into 60 zones, 60 zones, and each zone is at a difference of 6 degrees from the previous zone at the equator. Now, as you know, when you go towards the poles, the distance between two longitudes decreases. Okay. So we are saying with respect to the equator, the distance between two zones is 6 degrees. So if you extrapolate that, starting from the left or westmost extreme of India, that is Gujarat, the lies in 42 north, UTM 42 north, and as we go towards the extreme right, that is east, we have fringes of Arunachal Pradesh, which lies in 40, even in 47, UTM 47 north. So the entire India, if you talk about end to end, lies from 42 north to 47 north, and you can extrapolate the distance from minus 180 degrees at every 6-degree interval to find out in which longitude does your area lie, and that longitude lies in which UTM zone. Okay, so I hope I answered that question. Another question is, what is meant by pseudo-Mercator projection? Although this was not covered in my slides, but this is an interesting question because today all the maps that you see online, may it be Google Maps, may it be Bing Maps, or any other mapping platform, they use this projection system, the pseudo-Mercator projection system, to display the images that you see on the web, that you see on your browser. The EPSG code for this projection system is 3857. So this is pseudo-Mercator projection system is a derivative of the Mercator projection system, which is used for web mapping applications or for displaying maps on the web. Now, coming to the next question. In absence of any control points, is there a mechanism to georeference a topo sheet or a map? Arshia, this question is very vague because generally for any topo sheet or any map, if you have it in your hand or your system, you know where it belongs to on the ground. You can go to the ground and collect the GPS coordinates for some of the points which you can see on the map. These points that you have selected become your control points. So only in cases when the area is inaccessible, if the area is in an extreme location or is disturbed where you cannot go and collect the GPS locations, would you have an abscess of control points, and then it becomes very difficult to georeference any topo sheet. There are other artificial methods, but that require very strictly quality controlled extents to be available, which is beyond the scope of this basic QGIS demonstration. So we'll not go there. But yeah, to answer your question, no, it is very difficult to, or it is not possible to georeference a topo sheet without any control points. I am not aware of any such mechanism. What is the next question is again very important. What is the need of reprojection of georeferenced data? Once I have georeferenced my data, I have it in a projection system already which overlays with any other map, then why do I need to reproject it? Very good question. The genesis of this question lies back about 5-10 years back when the GIS softwares were not as user-friendly they are today. Today, what we did was we georeferenced a topo sheet in in a projection system lat long with datum WGS84. And then to check whether it is correctly georeferenced, I overlaid it with Google Maps. Now Google Maps is not in lat long WGS84. It is in this coordinate system with which one gentleman asked, known as pseudo Mercator projection system. Yet we were able to overlay them correctly and verify whether the output is right or wrong. That is because I was able to do that because of a functionality called on the fly transformation. That means once you open QGIS and you add a layer, all the subsequent layers that you add are reprojected on the fly, that is on the go, to the projection system of the first layer that you added. Okay, so there is no need to reproject all of these layers into a common projection system so that you can see whether they are all overlaid. Now to rephrase the answer, let's go to a time, let's imagine the GIS software is not able to overlay two data sets of different projection systems. Now how do you overlay them? You have to reproject one of them to the original projection system. Only then will you be able to view them together. Hence, reprojection is required to overlay the data sets correctly. That is one. Second requirement for georeferencing data sets is related to geometry or taking measurements. In most cases, when you take, let's say, distance or area measurements, you want that to be in metric quantities, meters or feet or things like that. X degrees as distance is not very useful, or x square degrees in terms of area is not useful at all. Hence, to make measurements, you require the data to be in a projected coordinate system or as in meters, and hence the reprojection of data is required. The next question is what is the difference between Everest and UTM projection? These are two different projection systems used for two different things. As must have been discussed in the projections class, different projection systems preserve different aspects like area, angle, shape. The UTM projection system was originated so that there can be a common projection system for the entire globe. If I want to represent different areas using the same projection system, then you can use the UTM projection system. Whereas the Everest projection system was used for areas which required or which were near to the Himalayas or the Everest mountain, so that the height values can be derived by keeping Everest as the baseline. So different projection systems were made for different purposes, and hence Everest and UTM and lat long and pseudo Mercator and so many, there are many projection systems. So all of them have different purposes, applications. The next question is, which UTM zone does Andaman and Nicobar Islands lie in? Very valid question. I think it lies in 45 North, UTM 45 North, which has the EPSG code 32645. That is 32645. This is the EPSG code for 45 degrees, 45 North UTM zone. Next question is QGIS 2.4 different from QGIS 2.10? The answer is no. The same slides or the same functions or same options that have been shown today are available in QGIS 2.10 also. There is no difference in the options which are shown. You will use the same options uh, as shown here to work on QGIS 2.10 also. There's so many questions. There is a question which says why there is no tool for georeferencing in vector data. Uh, so there is a tool, although it is not available uh, in the default installation of QGIS. There is a plugin called feature matching, which helps you match or georeference vector data. It requires some level of GIS knowledge already and skill. So if you are already a GIS person, you can search for this plugin called feature matching and use it to georeference your vector data sets. The next question is, which projection system is useful for a small area, any city, UTM or any other? As must have been discussed in the projections class, depending on what your application is, whether you want to preserve the shape, the area or the angle, you should select your projection system. In case you are lost and you wish to use one projection system that will be useful throughout your project or your course, you can use the UTM projection system for your area. It will serve the purpose for the time being. Is it possible to auto georeference? What is a plugin? What is a plugin? Okay. So plugins are ways to customize QGIS. So when the developers of QGIS, as you know, QGIS is a free and open source software. You can download it for free. So there are volunteers all across the globe, ordinary people like you and me who know little bit of programming, computer programming, can contribute to the development of QGIS or these open source projects. So now there is a core QGIS which has been developed over the past 10 years and which the developers do not want to allow to be mismanaged. So that core gets installed when you install QGIS on the and the rest of the functionality which you can also write is installed separately as a separate part called plugin. These have to be enabled separately so that they can be used and then disabled when not used. It may or may not interfere with the existing core functionality. Hence, it is kept separately and it is given the name plugin. Uh, some of the questions are not relevant for today's lecture. Google Earth attributes. These are not relevant to today's lecture, hence I'll not be taking them. Okay. EMR for GPS positioning must have been covered in depth in the uh, projection systems class. Geofencing is again something which is not. Okay, let's take the final question for the day. This question is, please elaborate on residual error values and what it means. Now, you may be aware of this technique called triangulation. Using this technique, the georeferencing is actually done. That means once you have identified 3 control points, effectively, if the 3 control points are correct, then all the rest of the points in your study area can be given a coordinate based on its distance from these 3 points. So if I have, so you may have seen some videos on how ships find their location. So there are 3 lighthouse or 3 radars which are continuously giving their location, and the ship takes its distance from these 3 known points and then finds its own location. Similarly, in georeferencing, when we are giving the 3 coordinates, all the rest of the coordinates are extrapolated from these known coordinates or control points. Once you give a 4th control point, the distance or the coordinate which it should be based on the existing 3 coordinates and the value which the user has entered, the root mean square between or the error between these 2 values will give me the residual error. If you add a 5th point, a 6th point, depending on the existing points, the location of the new point and the value which is entered by the user, the difference between them, the root mean square of the difference, x1 minus x2 square plus y1 minus y2 squared, the root over of this, which gives you the root mean square error, also known as the residual error, tells how much error is there in these control points. If there is very large error, let's say 14, 1500, that means the coordinates that you have given are incorrect or have been wrongly typed. The residual errors should theoretically be less than 1, where 1 here means 1 pixel. In terms of resolution or in terms of spatial resolution, if your 1 pixel is 5 meters, then in terms of distance, this residual error should be less than 5 meters. But ideally, in most cases, if you are doing it correctly, your residual error will always be less than 3rd decimal place, that is 0.001. Your residual error will always be less than 0.001. But theoretically, the residual error should be less than 1 pixel. Okay. That brings us to the end of the class. If you have any further questions, you may send me an email at this email address.